Let's discuss conductive heat transfer in this chapter. In order to understand conductive heat transfer and heat transfer in general, we really need to distinguish it from thermodynamics. They're related areas, but they are different. In thermodynamics, yes, we're interested in heat flow rates, but most of the time what we're really interested in is the quantity of energy that's transformed or moved or used, or how efficiently energy is used. But in heat transfer, we're actually not so much concerned with the amount usually as much as we are the rate. And so if you think about your coffee, you want to take your coffee to work and you put it in the thermos so that it stays warm. Maybe you want some coffee in the morning, but you hope to have some hot coffee at lunchtime. Well, what you really care about there is not so much how much heat leaves, because you really don't care how much you have to put into it, right? You don't care how much energy you have to put in to get the temperature up to where you want it. What you care about is the rate at which that energy leaks out, and that's why you buy the thermos, to reduce the rate of heat loss. So we use the symbol Q dot for the rate of heat loss, and of course it's just the amount of heat transfer per unit time. And of course the time shrinks down to an infinitesimal thing, so we can talk about the instantaneous rate. So my equation's not exactly true. You could put an integral and a delta t on the left hand side of Q dot, but you get the idea. It's just a rate of energy flow in the form of heat per time. Now another thing to define is something called heat flux. It's the rate of heat transfer per unit area, and it's also something that is quite important in heat transfer. So you can think of it as the flow rate of heat through a 1 unit area, say 1 square inch of surface of this thermos. Now, to give you an example of heat flux, if you have an area of 6 square meters, a wall that's 3 by 2 meters, and a heat flow rate through that entire wall of 24 watts, then you could calculate the heat flux as 24 watts divided by 6 square meters, which would be 4 watts per square meter. So each square meter has 4 watts as the rate of heat transfer through it. Now remember that heat transfer involves 3 mechanisms. There's convection, conduction, and radiation. Those are the only mechanisms that we're going to study for heat transfer as well. They're the only ones I know of. And so we'll talk about these, but don't forget that heat is only a form of energy that's being transferred between 2 systems, or maybe a system and its surroundings, by virtue of a temperature difference. So it's energy transfer that is due to a temperature difference. Now, to review quickly, why don't we try to recognize each equation and match it to its type or its mechanism of heat transfer. So pause the video and see if you can do this. So hopefully you realize that the last equation on the lower right hand corner is the radiation equation. It's the easiest one to recognize because it has temperature to the 4th power in it. So that one always has that one's always radiation. And so you should remember that that equation is the radiation equation, and remember that you're supposed to use temperatures in absolute units in that equation. The other 2 equations you can use relative units in because they both involve temperature differences. And so it doesn't matter whether it's absolute or relative units. Of course, if you want to, you can simply use absolute units to be safe. It will work just as well. But the way I remember is I know that H is a convective heat transfer coefficient and K is a thermal conductivity. So K goes with solids in my mind and H goes with fluids, whether it's a gas or a liquid. There is an example on page 382. I'd like you to go through it, but I'd like you to think of some modifications to it. Your author will go through and consider a wall that has convection and radiation transferring heat from one side of the wall to the other, so going through the wall's thickness. And he mentioned something called superinsulation. And superinsulation is not something that would be practical for installing in your home, for example. You might look at his calculations and see he goes from convection and radiation to just radiation by removing all of the gas in the wall, which itself would be very difficult in a home, right? Because then you'd have a vacuum. And he notes that basically the heat transfer rate is only cut in half roughly for reasonable temperatures that he gives. So he's trying to show you that radiation is a significant contributor to heat transfer in most cases. But then he goes on and talks about superinsulation, which involves not only a vacuum chamber, but basically a lot of strips of aluminum foil inside of it to reflect any photons that manage to come in. And it almost sounds like that this would be something that is useful in your home. It's not. It's something that's used in cryogenic distillation, where you have really low temperatures and you're trying to cool down air to the point where it liquefies so that you can separate it into its constituent components and then sell them off. Something like a company like Air Products does this. Now, the problem with cryogenic distillation is, number one, it takes quite a bit of energy to reduce the temperature of the air to the point where it liquefies. And so any thermal energy from the surrounding environment that finds its way back in and infiltrates back into this super cold liquid air will raise the temperature, will boil it off again. And so you've got to really avoid that. So they actually do use super insulation in those processes, and it is practical in those processes, about the only way to do it. But for an everyday material, well, not really everyday, but something that is a little more obtainable, there is a material called Aerogel. And Aerogel, although it has about 10 times the effective thermal conductivity of what your author calls super insulation, it is something that actually is more practical, even though it's still a relatively exotic material. Aerogel is interesting because you can perform some very neat demonstrations with it. You can put your hand on one side, aerogel in the middle, and a flame on the other side, and the flame will not burn your hand because the aerogel has such low thermal conductivity. You can put the aerogel above a Bunsen burner, put crayons on top, which are relatively low melting wax, low temperature melting wax, and the crayons do not melt. So it's a really interesting demonstration, and obviously the aerogel does not conduct heat hardly at all. And so I would suggest you consider aerogel instead of super insulation in the example. But the example is worth going through. As a matter of fact, I work examples from the problems given at the end of the chapter because I want you to go through the examples within the body of the chapter. I feel like that if you will go through both of those, maybe you'll learn more, because I know someone else will have a different approach to problems than I have and may explain it a different way. And so your author's explanations may help you understand seeing things from a different angle.